so many versions of, so you think you know how to do it, but we can't.
Cool. Well, let's figure it out then.
Yeah. Well, okay.
Just be violent. All right. So a projectile is fired from the edge of a cliff into the sea some distance away from a 112 meter tall vertical cliff edge. Knowing that the projectile leaves the cliff edge with an initial velocity of 36.2 meters per second at an angle of 67 degrees from the horizontal, and the object experiences no appreciable air resistance, calculate the distance at which the projectile falls into the sea. Cool. So yeah, like you said, you'll see this type of setup, over and over again in physics.
Yeah.
And sometimes there will be, little twists with like what information it gives you or what information it asks for, but the basis of it is the same. It's always a projectile motion question. So I always like to start with a picture and then start labeling the things that I know and the things that I don't know. So we know here's the edge of our cliff. It's 122 meters tall.
112?
112.
Oh, it was 112?
Yep.
Good catch. 112 meters tall. And we're firing it at, what angle did it say?
67.
So kind of a steeper angle. So 67 degrees. And its initial velocity is
36.2 meters per second.
meters per second. Cool. So we know that it's going to follow some path like that. So we're most interested in this initial point and this final point. So let's go ahead and use variables to describe both those 2 points. So here we can describe it with a y naught and an x naught. That'll tell us where it is in space. And then we can also describe it with a v naught y, a v naught x, and a t naught. And then down here we'd use the exact same set of variables, but without the naught sign, because these would be the final values. So we'd have y, x, vy, vx, and t. And then also there's going to be acceleration, but only in which dimension?
X.
Only in the y dimension, right? Because gravity pulls down. And it said that there was no air resistance or anything that we would need to worry about.
If there was air resistance, there would be acceleration or deceleration?
Yeah, in real life, when we throw a baseball or something, it's going to slow down in the x direction because it's going to be going up against, air molecules, which are going to slow it down. But in 105, we usually just don't worry about that. Because compared to gravity, that stuff's pretty small. So we can say a sub y, just to remind ourselves that this only happens in the y dimension, and that's going to be negative 9.81 meters per second squared. Okay, so now let's start filling in other values that we're aware of. So what would be a good number to put for y naught? Where is our object in space?
112.
Good. So that's 112 meters above the water. So we can call the water our 0 mark. So let's go ahead and put a 0 over here. And our cliff would be the 112 meters above. X naught, what do we want to call that?
0.
Yeah, we can technically call it whatever we want, but an intelligent decision would be to call it 0 because that's an easy number to work with. T naught, what do we always call? 0 seconds. So now our velocity, we originally were given velocity with this weird angle, and so we want to split it into x and y components. And so we can do that by saying, well, it's going to to the right this much, and it's going up this much. So we've just created a little right triangle. We know the magnitude of our hypotenuse, and we know an angle, so we can use trig functions to figure out our y component and our x component. So we can say sine of 67 degrees multiplied by our hypotenuse, which is 36.2, will equal our v naught in the y dimension. And then we can do the exact same thing with cosine to find our v naught in the x direction. Any questions there? You guys have done that a lot by now, I'm sure. Cool, so now we have values that we can plug in to our diagram for v naught y and v naught x.